The LCROSS mission launched in June of this year, and that really set the pole we had to go to. It's springtime in the southern hemisphere right now, and so we have good lighting. What you see in the video here is the lunar South Pole, a variety of craters down there that we had to consider. What we had to do over the last year and a half, 2 years, was pick one of these to go to. And what you see here are finalists that we've used Kaguya data and Chandrayaan data and LRO data to help us actually determine which one. Over the last 3 months in particular, LRO has been very active in observing these specific craters for us. What you see here is a radar image from the Goldstone radar dishes in California of the South Pole. You can see a variety of craters down there. We looked at such craters as Shackleton, Shoemaker, Hayworth, but they had to meet certain criteria, and I'll tell you what those criteria are in a moment. And the crater we finally selected is shown here now. It's Cabeus A. Cabeus A is at about 81 degrees south. It's a little bit off the South Pole. It's a relatively large crater, about 40 kilometers across. And as we zoom in and look at it here, you can see it has a rather large crater along its rim, and that is where we think the sweet spot exists. We're going to continue to refine our understanding of this crater now that we've selected it with detailed observations from LRO, and continue as we get closer and closer to impact, refine the exact position within this crater that we are going to impact. We already have a very good idea where it is, but we have the fortunate ability to refine that in the next couple weeks. The next image here shows the topography of this crater, Cabeus A, as seen from the Goldstone radar dishes in California. Yellow is low, blue is high. Topography is really important because it really determines the illumination within the crater. Sunlight is blocked by topography, and you can see here the black areas are actually shadows cast by the radar. The topography is blocking the radar signal, and we see it as shadows. The sun does the same thing. So really important to the LCROSS mission success is to get the ejecta, the dirt that's thrown up out of the crater, into sunlight. And that's what we want to do, is get dirt into sunlight. So that was one of the principal aspects that we looked at in terms of selecting a crater. This also affects the Earth observability. How observable is the ejecta and the impact from Earth? And I'll comment on that a little bit more later. Also from this topography, like this, and topography that we got from the Selene mission and from LRO, is slopes and roughness. We want to hit a nice, flat, fluffy place. The more flat, the fluffier it is, the more material gets thrown up in a very predictable way. If we hit on angles and slopes or blockiness, that affects the ejecta and how it flies upward in unpredictable ways. So we want to avoid that. What you see here in this graphic are slopes derived from that altimetry, that topography image you just saw. Blues are low slopes. These are slopes of just a few degrees, less than 5 degrees, whereas the yellows and the blues are slopes as much as 20 or 30 degrees. We want to avoid those steep slopes. Luckily, in most of the craters we looked at, we considered, they had large, flat, even floors. And the data we've looked at, even at scales as small as 40 to 50 meters, we've been able to find areas that are relatively smooth, boulder-free, and flat. We're using image data from the terrain camera on Selene and from LRO to actually see down into these craters using just scattered light, just earthshine light, and be able to pick out individual boulders that we want to avoid. So the process is ongoing, but we've been able to find very good candidate target locations. Specifically to this crater, Cabeus A, the conditions look very ideal. One of the more important criteria, of course, is its potential association with water ice. We don't want to go someplace dry, even if it throws up a lot of material. So how do we know if a place is wet or dry? The data that we have, the most reliable data, is neutron data. Neutrons are emitted from the moon. By observing how many neutrons come up from different places on the moon, you can determine if there's hydrogen there. And this is really one of the first clues from Lunar Prospector over 11 years ago now that there was potentially water at the poles of the moon. there have been detected hydrogen concentrations at the poles of the moon, and that's really what we're using as a guide to selecting crater as well. Lunar Prospector's observing footprint, the resolution of the data it took was very coarse, 40 to 70 kilometers. The LRO instrument has much higher resolution. It has 10-kilometer resolution. That crater I showed you was about 40 kilometers across. It's about 60 miles or so. The footprint that LRO can see, measure neutrons, is about a third of the size of that crater or a little bit less. So we can actually tell where in that crater the hydrogen is piled up, so to speak. We can also use analysis and look at older data sets from Lunar Prospector to really understand where the hydrogen is, assuming certain things about its potential distribution. This graphic here shows some analysis that has been done by colleagues on our science team on LCROSS, showing the potential water ice concentration in the craters that I've just discussed. The color coding indicates the concentration, potential concentration of water, blue being about 2% water. That's a significant amount of water, actually, for the moon. The gray area is the topography of the moon, and you can see Caballase, our target area, circled there, and we can actually zoom in on that a little bit, and you can see that dark blue dot there. That's in that large crater to the edge of Caballase. That's what we're really looking at and considering right now as what I called our sweet spot. That's really where we think we need to go. You can see this analysis suggests there's quite a bit of water in there. It is consistent with observations from Lunar Prospector, from LRO, the neutron measurements from LRO, all indicate that there's quite a bit of hydrogen in this area. LCROSS wants to understand what that hydrogen is. So the last criteria really is observing from Earth. We wanted to make a very robust observation campaign and have multiple assets looking at this. You're going to hear more about this specifically from Dr. Hellman in a second. But in terms of selecting a crater, we had to make sure it had good observability to Earth. And so the next movie will show some observations that were made about a month ago from one of our collaborators in New Mexico. This is from the Apache Point Observatory. These are colleagues from New Mexico and Marshall Space Flight Center who made these observations. This is with a camera on a 24-inch telescope, and you can see Caballase there, Caballase shown circled. It is very observable from Earth. This is again one of the reasons we selected it. It gets good illumination and is very observable. We'll have lots of assets looking in this region during the impact, so we'll have lots of eyes on it. So with that, and to expand on that, I'll hand it over to Jen, and she's going to tell you about the observation campaign.
Great. Thanks, Tony. So thank you very much for the opportunity.